Okay, welcome to Lecture 20 of 53237323 Mobile Sensing and Learning and Control. How's everyone doing? Good? Feel good? Is it because the sun's out today? Everyone's kind of like giddy and happy after, I don't know, was the sun out this weekend? No. Well, so this is kind of good. Someone's like, huh? This is good. This is good. So A4 and A5 are now turned in. I'm about to assign A6 today, so everyone's going to find out what it is. Not that you don't already know. So we've been talking about most of the things. Everything after essentially this week and maybe one lecture next week is going to be bonus lecturing, where I am taking materials and putting it together for a lecture that is essentially for iOS development, but you'll have everything that you need to do with the final project. The week leading up to the final project, I'm out of town. That's on the schedule, so there's no class that week. So you can go ahead and take a look at the schedule and see how that looks. Okay, course logistics. A4 grades really are coming, I promise. They're just not up there yet. A6 is going to be due next week. We assign A2 today. The problem with that is that normally things are due on Friday, and next week is Good Friday. And it's a university holiday, and nothing is going to be due on Friday. So it's going to be due on Thursday. Here's the problem with making it due on Monday. Like, if I make it due on Thursday, you guys are you'll get it in on time. Like, you'll make it Thursday. If I make it due Monday, you're going to be working through Easter to try and finish off this assignment to have it be due on Monday.
He knows this so well. No other professor thinks that way. They all think like extra time means you're going to spend the extra time. He's got it down. He knows that moving the due date matters.
It's kind of a forcing function for getting you guys to work on the proposal and to get things ready and start working on the final project, because the final project in this class is a beast, and I want you to have 3 weeks to sit down and be able to do it, right? And I'd like A6 to be the first draft of this, of essentially the final project that you have. I'm going to say it's due Thursday. Okay? It's due Thursday of next week. The only problem with that is that if you can show me a demo of it working on Wednesday, that would be great. Because I'm not going to be here Thursday. I've got some family stuff that I have to go up and sit in a hospital for a couple of days. Not for me. But I won't be around is the thing. So if you can upload a video for working, if you don't show me on Wednesday, that'd be wonderful. Okay? So the final project proposal is also due. It is, I encourage you to actually make it a website, because I'm essentially wanting you guys to put together a website for what the final project is going to be. Put a video together, which is something like you would see on Kickstarter, which is selling your application. It's only going to be a little more involved. It's not like going to be something you see on Kickstarter, because I want to know how you implemented it, right? I want you to give me the details on how you evaluated it and these milestones that you were trying to hit. But having a really, really cool video to show me would, essentially, with a video, I feel like you can make so much more than a final project report. There's so much more that you can tell me. And I think it's more fun, and I think it makes a lot more sense for an application development class.
So is the proposal still due Friday, or is that due Thursday?
The proposal is due Thursday. I don't want to make anything due on Friday because it's a university holiday. The project proposal is also like 1 page of text that you can put up on a website, right? So start putting together your ideas for that, what it's going to look like, and put together the milestones that you're going to hit for the project. You need 4 or more constraints that you need to meet, okay, and how you're going to evaluate them, all right? You can just put a text together and submit it to Blackboard, or you can give me a link to the website. Questions?
So should we try to get some feedback from you before that, or are you going to kind of provide feedback and we can adjust the proposal after that?
If you're encouraged to get feedback beforehand, I will give you feedback on the draft you turn in as well. I would recommend that. Yeah, just even shooting me an email, say, hey, these are the constraints that we're looking at. What do you think? And then I can kind of give you some guidance on making them harder. Or usually it's me telling you that take constraints off of a final project, because almost inevitably everyone wants to bite off more than they can chew. Okay? Okay. So that's that. Assignment 6. I want you to make this the first iteration of the final project. I am also giving you so much code that is part of what's due for assignment 6 that I don't know. I mean, the sum total of code that you would have to write for this is going to be something like 100 lines. Okay? It's not bad. But there is a creativity component to it, which maybe makes it hard. So it has two modules, Module A and Module B. In Module A, I want you to create an iOS application using the HTTP example that we had from last time, and we'll make some updates to it. And essentially, it collects some form of low throughput data for processing. That can be audio data, or video data, or motion data, or something that you're sensing from the Arduino. It's just data, right? That's sampled at something greater than 1 second, okay? It could be once per minute. I want you to upload some of that feature data with a label to the web server that we create. And then I want you to train a model for using that data to predict whatever labels you're sending up from the web server. And then you can ask the web server for predictions based on data that you have that's unlabeled. So this gives you a lot of free reign for things that you can do. So if you were doing a final project where you needed to, I don't know, figure something out from an audio field, what you could be doing is you could be reading it off the microphone, right? Getting some features from that, whether it be like, oh, okay, I'm going to take this audio data, I'm going to take the minimum, the maximum of it, and the mean, or maybe some other statistics. I'm going to put that together in a feature vector. And then once every 5 seconds, I'm going to transmit those up to the server, right? And then I'm going to have some calibration protocol where I'm sending up labels, right? So maybe this is when I'm playing music, or maybe this is when I am, I don't know, tapping on the desk, right? And the label that comes up is either playing music, tapping on desk, or silence, right? You'll upload it to the web server, and you'll tell the web server to train that model. And then when you have data where you don't know what it is, some user is transmitting some data, they upload it, and then it provides a label back to you what that audio data is. Okay? Try and make it revolve around what the final project that you're going to work on will be. Okay? So if you have an idea for a final project and part of that is actually needing to do some machine learning, this would be the way to do it. Okay? For Module B, I want you to update both the HTTP example and the Tornado web server so that you can specify the type of machine learning that you want your web server to use to provide you predictions. Okay? I want you to implement at least 2 different types of machine learning models. All right? So for example, if you use the support vector machine and k-nearest neighbors, and you'll know what that is by the end of this lecture, then that would suffice. That would meet the quality, essentially this constraint. I want you to compare the accuracy of those 2 different models as well. Right? So you can tell which one is better. Should I be using KNN or should I be using SVM? An extra credit, if you can make the training of the model on the Tornado IO loop non-blocking, you get extra credit for that. Okay? Or if you implement some kind of authentication in Tornado and in your iOS application, HTTP authentication. Okay, so essentially here's what assignment looks like. You've got your web server, and essentially you've got your iPhone application, and what it's going to do is it's going to request a dataset ID from your web server. Say, hey, I need a new ID so that I can start uploading data. And then it's going to upload whatever data that you are collecting, right? Whatever you think is interesting and the labels for it. So it's going to have features and labels. It's going to provide those examples and save them into the web server. Then what it's going to do is it's going to say, hey, web server, would you train a model on that data? and it will train a model. And now when I have new data that comes along, so I collect new data on my iPhone application, I stream it up to the web server, I request a prediction, and it sends that prediction back down to me. And then I have what it thinks that label is. All of the uploads are handled in a JSON format. Okay, they're all HTTP requests where JSON is sent up, which is the feature data. If you look on Blackboard, most of this code is actually already implemented for you in the HTTP example and in the Python Tornado web server examples that it's already on Blackboard right now. It's all there. You just have to run it. And we will run it probably next lecture. And I'll show you exactly what it looks like. Right? So for Module A, you won't need to do anything to this web server. It is already saving all of the data. It's already creating a machine learning model. It's already, giving you new data set IDs. You just have to figure out what data you want to send up to the server that you want to predict on. Okay? Has anyone ever seen this model before, where you're taking data, you're sending it up to a web server, and you're asking for a prediction from the web server? No? Nothing? Anybody ever seen Google's cloud platform, their prediction API? No? It's essentially this. It's exactly what I'm having you do for A6. It's, hey, upload some data, right? Normally the data that you're uploading is some features from an email client, right? So that you can filter between spam, junk mail, and real mail, or important and not important, right? So that's a good old prediction anyway. Has anyone ever seen this company called BigML? No? They use the same exact thing, except they charge you for every time you want to predict something, right? So you upload a bunch of data. They're like, awesome. You have 100 predictions for free in a month, right? And it's like, if you want more predictions, you can pay for it, right? And it's a nice little business model that they've built out. And they've made a lot of money.
Is the ML machine learning?
It is, yeah.
Not markup language.
It is not markup language.
Like every other ML.
It is ML in the terms of machine learning, right? And it's big ML because it's big data, right? Big data. Let's jump on that bandwagon, right? I'm going to teach you a toolkit called scikit-learn. We'll get into it. Essentially, what it is this big ML. They have a lot of things. It's like, hey, you can do this from your web browser, or they've got a Python code base, or look, they've got something where you can actually do this in iOS, right? And you can upload, there's all these different URLs where you're uploading data, or you're uploading labels, or you're requesting a prediction. So the way that it works is essentially you set up a data source inside of BigML, and you upload some data into it with labels, and you create this thing called a data set. What do I mean by a data set? It's essentially a database, but it's got some structure to it. There's a prediction, there's feature data and a label for each feature. Okay, that's going to be a data set. In machine learning, that's kind of what a data set means, right? Normally, a data set could be almost anything. But if you create this data set, then you can generate predictions, and they will charge you for it, right? And the way that it does it is actually use a tree learning algorithm. So there's different models that you can create, and we'll go over each of those. Hey, you made it.
I did. Almost.
Just kidding.
Almost.
I'm sorry.
Almost didn't.
Sorry. Carly sent me an email right before class that car was getting towed.
I just lost my keys inside, so it's fine.
Okay.
Truthfully,
That's
I'm
good.
for you.
That's good. You know what I think is awesome? No one's phone has gone off in class yet.
Oh man,
Now it's going to happen. Okay, so here's what happens if someone's phone goes off. I get to answer it. Okay?
Did you see the April Fool's prank that went viral this weekend?
No, I haven't seen
It
it.
was the same kind of thing, but they had to answer it on speakerphone. They set it up so like one of their friends called and acted like it was a pregnancy, like working on the group. And the professor just stayed there. I'm so sorry.
That's really terrible. That's really terrible. But we're all laughing, so okay. So that is essentially what I'm having you build for A6. Are there any questions about what I'm trying to have you build? It's a machine learning web server that you can charge people to use. Okay? Good? Question.
I was curious about the specifications of using MongoDB and Python and Tornado.
Yep.
I was just curious why only those.
Why only those?
Yeah.
Because I've written the code for you, and they're already set up to use.
Okay.
You certainly don't have to. I like the idea of using Tornado and MongoDB because they've got a lot of usage in industry right now, especially MongoDB.
Really?
Yeah.
Okay. Yeah.
I mean, you can
Right on.
you can use your own web server, right, if you wanted to. You just have to implement it to be able to insert these into MongoDB and run some of the queries. I also really like scikit-learn, which is implemented in Python, which we're going to learn about today.
Okay.
And it hooks up really, really easily and really well with Tornado and MongoDB.
So Python kind of hooks them all together.
Yeah, it's the glue. Good questions. Good questions. If you ever wonder why I'm teaching you something, ask me. If I don't have a reason, we'll learn something else. Okay? All right. So, intro to machine learning, we're going to talk very, very briefly about NumPy and SciPy, and then we're going to talk about scikit-learn. If you're using iOS with Python, what should we name that library? We got NumPy, SciPy.
iOS Pie.
How about Apple Pie?
Nice.
It's already taken. I know. What are you going to do? So essentially, by the end of this lecture, this is what I want you to know. I want you to know what machine learning is. Very kind of intuitive overview of what is this thing. How many of you guys have heard the term machine learning? How many people know what it is? Feel comfortable explaining it? Yeah, I'm not going to make you explain it. Who feels comfortable explaining it?
I mean, I have a general idea.
You have a general idea. Okay. By the end of this lecture, I want everyone to be able to say, yeah, I know what machine learning is. I want you to know the keywords that are used in machine learning, because that's 60% of the battle, is knowing the keywords in an area. What's that?
That is so true.
It is. I'm not kidding. I want you to know about a machine learning toolkit to be able to use machine learning even though you don't understand or necessarily know all of the math behind the machine learning that's there. Because you know what? Not very many people do know all of the math behind it, right? But they can still use it because they have an intuition about what it does. And I want you to lose whatever barrier you had coming into this class to being able to not use machine learning, because all of you can use machine learning, and hopefully this lecture will just be a primer for it. You can get on YouTube and figure out what machine learning is, okay? It's not as hard as you think. Or maybe you think it's easy, and it is. Okay? So what is machine learning? So the definition of machine from Google is an apparatus using or applying mechanical power or having several parts, or also a coin-operated dispenser. We're going to use the former definition. Okay, or any device that transmits a force or directs its application. Okay, so machine. What is learning? The acquisition of knowledge through experience. Okay, so what is machine learning? It's how you teach a computer to learn something through experiences. And through experiences is the kind of key topic in here. How do you give a machine experience so that it has knowledge on how to predict something? Okay. So how many guys have heard the term artificial intelligence? What is artificial intelligence?
It's a computer sort of thinking like a human.
Yeah.
It's a machine.
How to make a machine act intelligently. That's artificial intelligence, right? So that includes a lot of different things, right? That includes things like the Terminator. How to teach a computer to follow a set of rules. It could be that simple, right? That could be artificial intelligence. It could be how to teach a computer to play chess. Or just any game in general, right? So any kind of knowledge or logic behind a gaming application could be considered artificial intelligence. Machine learning is a strict subset of artificial intelligence. So if artificial intelligence is this big kind of encompassing thing right here, machine learning is a subset of that. And it's how to teach a machine to learn by example. So you're going to teach from examples here. This would be something like, oh, I'm going to create a model. Or I'm going to predict something. How many of you guys have heard the term data mining? Yeah, data mining. Okay. So the difference between machine learning and data mining is pretty small, to be honest. Okay. One of the definitions for data mining is how to detect patterns, normally for people to interpret those patterns, right? Data mining and machine learning are both subsets of artificial intelligence, and 90% of data mining comes from machine learning. Okay, and there's a little kind of bit, which is visualization and things that are in data mining, clustering, that aren't really included as type of machine learning, right? So machine learning is teaching a computer. Data mining is going through a lot of data and coming up with patterns so that a human can look at it and make some sense of it. All right? Both of them are subsets of artificial intelligence. Okay? Both of them could be creating a model, but in data mining, a lot of times what's happening is you're clustering data together to come up with a feature. Right? You're just like, oh, I've got all this data. I have no labels for it, but I want to cluster inside of it and get some knowledge from it. Help me visualize. Machine learning. So what examples can we use to teach a machine? How about this? We're going to take some features, and we're going to take labels. These are the examples that I'm talking about that we're going to use in a machine. If we're going to teach something to a machine, I need something that I'm going to predict on and a value that's an example, right? So once I have these examples, that's what I'm going to use. That's what we know. What we want to know are the predictions, okay? I'm sorry that I'm going painstakingly through this. But let's say we are Netflix, okay? And the features that we have are some genres, some actors, some other things that we can pull from different videos that exist out there, right? Different movies. The labels that we have are whether or not some person likes or dislikes these movies, right? So based on those labels and features for that person, I want to predict whether or not they're going to like this last movie, right? So I would come up with a machine learning model that takes into account all of these features, genre, actors, words used in the movie, and I'm going to kind of take these labels and build something to detect whether or not they would or would not like this movie. And the only thing that I can get out of this is whether you like or dislike this movie, right? So based on this right here, you might also be able to tell something else about a person, such as, are they an adolescent male, based on the movies that you see here. All right? But unless you specifically have examples of the genres and things that an adolescent male would like, you're not going to be able to predict that. The only thing that this machine learning model can predict is likes and dislikes. Fair enough? So if you don't have a label for it, you can't teach it through machine learning. So let's talk about features. What do I mean by a feature? Actually, what I'm talking about here are feature vectors, right? So a classic example of this is the iris dataset. All right, you guys seen the iris dataset before? Anybody? Yes? You got the iris dataset. Yeah. It was created in 1988. We had basically, where have you seen this before? Is this in data mining? Okay. So we've got the iris dataset that's here. There are three different types of iris flowers that we're trying to predict: the setosa, the versicolor, and the virginica. Okay, these are actually not very good representation examples because a lot of times these iris they look identical to one another, right? The same colors, same kind of color scheme, right? But inside of this data set, what we have are 4 features that were collected from 150 different examples, right? And those 4 features are the sepal length of the flower in centimeters, the sepal width in centimeters, and then the petal length and the petal width, okay? So one of the feature vectors, one of the examples might look like this, right? Where I have the sepal length is equal to 5.1, and then the petal width over here is equal to 0.2 centimeters. Okay? So this right here is what I'm talking about when I say I have a feature vector. Right? It's just one vector of information. So 3 of these examples, I might have, okay, this is a setosa, this is a versicolor, and this is virginica, based on those examples. Inside of this classic iris data set, I have 50 examples of each flower that are there. So someone went out in 1988, grabbed 50 of these flowers, measured the different petal widths, sepal widths, and lengths, and then put it together inside of a data set. Okay? So this would be a feature vector. So when you want to run, based on those feature vectors, what we want to do is predict. Now say, okay, I measure this flower, it comes in, and I measure these 4 features. Now that I have this unknown feature, I want to figure out where it came from. One of the first things that I'm going to do when I have a data set is visualize the features. Okay? How many of you guys have ever seen a box plot before? What's a box plot?
There's like different features for each maximum, minimum, median, and it's 75 and 25%.
That's exactly right. That's 100% correct. So essentially what you said was, okay, so for basically, if I would just take this class, this versicolor class, and I were to look at the 4 different features where I have the length, width of the sepal, and then the petal length and width down here. I could essentially look through this data set and put together this red line would be the median value, right? And then I would have, okay, this is the 75th percentile, this is the 25th percentile, right? So 50% of my data is going to sit right inside of this box. And then I've got these whiskers that come out right here that tell me anything on the outside of those whiskers would be considered an outlier based on this data that I have right here. Right? So based on the sepal length for versicolor, I get this. It's a way of visualizing essentially a histogram, a distribution, right? Except in one line. Very, very compact way of visualizing it, right? So here's versicolor, here's virginica, and here's setosa right here, okay? Are any of these features that I'm looking up here, would they be good for predicting the different flowers that are there? Yeah? What's the strategy that I would use right here for trying to select which features I might use?
You want to find the column that doesn't like overlap.
Yeah, non-overlapping, right? So if I were to go down here, what about this is sepal length right here? Is this a good feature?
No.
Is it not?
Well,
It's maybe not the best feature. It's
it
okay.
can tell you whether it's setosa or not. Yeah, versicolor and virginica are so similar.
Yeah, so these are really, really similar to one another, looking at those, the first one. But this right here is actually pretty different from the other. So based on that, I could probably separate completely the setosa and the versicolor or virginic flowers. Okay, but there's also a couple of different features in here that would work for separation. Right? So the main thing that we're worried about when we're looking at visualizing these features is based on these features and based on the classes for each of the features, how separable are each of the classes, right? Now this is a one-dimensional view. This is just telling me if I were to use one feature, could I separate these classes, right? What's a better way of looking at how separable things are? I've got feature vectors and labels for each. Multiple features, absolutely. So instead of just saying I've got one feature and there's another feature here, and are they separable this way, maybe a combination of features, if I got this feature and that one, makes it actually separable, right? So if I were to visualize the features this way, where I plot x1 versus x2, so sepal width versus sepal length, and every single 2-tuple combination I can plot versus each other, right? And then I'm going to color code these. Blue will be setosa, and then I'll have versicolor and virginica, which are similarly colored, and that's okay because they're similarly clustered together in all of these plots. Okay? But essentially, this is telling you that, yeah, I mean, if you can draw a line that separates these two classes, you can come up with a classifier, right? Or if I can draw something around one class, I can use that to build a classifier, right? Anything that's inside of that bound that I draw, I'm going to classify as setosa, right? Here it's a little bit tougher. I could maybe draw like a line right here. It won't be perfect. Okay? So this is a pretty good way of visualizing things together. Am I missing out on anything?
I mean, the combination of the three is going to give you more accurate.
Combination of 3 features, right? Yeah, let's see what it looks like. So instead of taking those 2 dimensions, what if I were to take 3 dimensions, right? And if I can now draw a sphere around the different features that are there, or some kind of what do they call it? Ellipsoid, right? Around the cluster of data, right? Or a box, right? right? Then when I'm actually going around and looking at the data for my iris data, I can kind of go around. I can see setosis down here, super easy to do. I can almost, like any feature can separate that out. And this other one, I can kind of draw maybe a plane in between the black and the blue to try and separate the versicolor and virginica. You can kind of now see it in 3 dimensions, right? On what that plane might look like. It's not going to be exactly perfect. They're still right up against each other for what they look like. But I can probably come up with a rectangle inside of there. Okay. What about 4 dimensions? Better. How do I visualize that? You're going to say hypercube, and I'm going to disagree with you. How many people have ever looked at something in 4D? No one. Anyone who tells you that they looked at something in 4D is blowing smoke somewhere, okay? No one, at least the masses of people, cannot visualize something in 4 dimensions. You can teach yourself to kind of look at some of the cues and stuff, but it is extremely non-intuitive to look at something in 4 dimensions and think that you're going to get something out of it. I have seen some demonstrations where they take a 4th dimension, which is time, and they say, okay, I'm going to look at a 3D plot, and the 4th dimension of this other data will be time and forward. So you can kind of move it around and you can go forward in time, and that's the 4th dimension. And that's kind of the brain can kind of internalize that. It's not really that good at it. It's still not that good at it. Okay? So we have to rely on basically some of the principles that we learn from looking at things in 3 dimensions and hope that they carry over into higher dimensions. Because there's no way to visualize anything above 3 dimensions. Not well. We can do a lot of 3D plots and do things. Does anybody disagree with me on that? Come with me on that? No? Sometimes I get people that want to fight with me on the 4D stuff.
Well, just like one thing that could be, I mean, it's not like a visual thing, but for example, when storing data, when you go to bigger dimensions, a way to visualize it would be like, you know how you have like one element, and then you have another dimension which is like a line, and you have like something like that. But then you think how it's stored in memory, and it's actually just a list of like bigger lists and bigger lists and bigger lists. So you could just think of it as like an addition of all like more and more sets of data.
It's true. Yeah. Yeah, essentially what we have here, the only thing that we can visualize is if we have 4 dimensions, and this iris set is 4-dimensional. A 3-dimensional view of the iris data is a projection from 4D space down into 3D space. In the same way that if we were to take this cube that we're looking at and just look at it in terms of the 2, that's a projection down onto 2D space, right? The second that we take it up to 3D space, there might be separability inside that 3D space that we didn't see before. The second that we take it up to 4D space, right, there might have been a cluster that was just one on top of the other in 3D space that now separates inside of 4D space. I can't show you what that looks like, okay? Because the only thing that our mind can internalize is 3D space. It's the only thing that we were evolved to recognize, right? It wouldn't make sense to see things in 4D. Okay. That was just my aside. Okay, so the most common things to have for features are numeric data, usually continuous data or binary data, right? Where it's like a number, 0 or 1, right? Or it's an integer value, right? So those are the most common types of features that you would use. Can you guys give me an example of features? Give me an example. I just want to know that you're listening. Gender, bam, 0 or 1. That's a binary. Well, I'm trying to think of edge cases in which like the assumptions that you put into your features, they come back to haunt you later on. Okay? So yeah, maybe you would, like, let's say this was survey data, right? 0, 1, right? So you have the gender as male or female, and then unknown, right? You kind of leave yourself some leeway at the very end, right? For maybe, you don't know what it is. It could be they just didn't want to enter whether or not they were male or female, and now this is missing data. Okay? Give me one more example which is continuous. Did you say height? Yeah, absolutely. Height. Age. Alcohol content. All right? Why did I say that? Because when you're trying to classify different wines, right? And you take a bunch of people, then they rate wines. They give it the 98 or the 99% rating. The number one predictor for that is alcohol content inside of the wine, and you can show that statistically.
So the more alcohol content, the better?
Yes.
Yeah.
Absolutely. Yes. Okay. That might be that's just correlated with a preference for some of the taste that's in the wine. Okay. You don't show causality here. All we're doing is exploiting correlations. All right? We don't know which causes the other. All we know is that they go the same way. Therefore, we're going to learn that they go the same way. Okay? You could also take it and quantize your vectors, right? So let's say you have continuous data, which is alcohol content, but I want to bin that down, right? I don't want the alcohol content to be, 0 to 5.6% or 8% or whatever it is for wine. I want to bin that down into an integer value, say like 1, 2, 3, 4, 5, 6, 7%, right? That would be a form of quantizing a continuous value down into a set of categories, right? So that's a keyword. There's also something, let's say you're doing classification on document data. You guys do a lot of classification with document data for data mining? Hospital data. Okay. Did you guys talk about the bag of words model?
Not, I mean, I've done that in some other classes, like information retrieval,
Right.
and the TF-IDF.
Right. Okay, good. So TF-IDF was in data structures. Good. Awesome. So there's this bag of words model. Let's say you have a bunch of documents, right? And you want to turn each document, and this is a document in terms of like an article, like newspaper documents, not a document in terms of MongoDB. Well, I guess it could be the same thing. A bag of words model would say, okay, let's count the frequency of words in every single document that we have. And we'll just save the frequency, right? And the number of times I see the word, I don't know, Twitter, right? So if I see the word Twitter, 1,000 times in this document, that's meaningful. If I look at, the word Twitter in another document, it happens twice or 0 times, that's usually a pretty good predictor for predicting what the topic of that document is without having a human read it. Okay? Have you guys ever seen a machine learning summary of text? It used to be really awful. Now it's pretty good. Right? Like you can, so some of the things that you read online were not written by a human. They're aggregating data from like the NASDAQ and this different things, and it said, and then they put it together with different words that essentially string it together, and it looks like a human written article. Right? It's just a paragraph of text that tells you what happened during the day, and Apple did this and what it kind of means, and they even make some conclusions and things. A human never wrote that. A human never even looked at it before it was printed out to press. Okay, but it showed up on your mobile device. How did they do that? Machine learning, with a really good model for how to put that text together, and a lot of examples of good writers. Graphs. You guys ever built a graph? Of course you have. You're computer scientists. Are you kidding me? You've built a graph before. Okay? So if you've got data and you start with one data point and you start making connections inside of your graph space, each of those clusters, right? Maybe you start clustering things in the graph into one node. Each of those nodes could become a feature that you use. All right? In machine learning, this is something called manifold learning. You guys actually know exactly what it is if you've ever clustered data together, right? It's a really, really hot topic right now. And it works really well. When you take all of your feature space and you're like, I have no idea what I want to use, I'm going to run a graph on it, and each of these nodes now is going to become a feature for all of the different labels that I have.
You're talking about like an XY plane graph or like
Yeah.
a tree graph?
Like a tree.
Like a tree.
I'm actually talking about both, because you could do it either way. And we come up with a feature. As long as you have a leaf node somewhere. Right? Or a node, even a node in the middle, you could use as a feature. Right? Take the data mining class. Are you guys going over this in data mining? Yeah? A little bit. Okay. I was surprised at TF-IDF, but if you're using medical data, it's another application space where.
You do a lot of search engine
Is it the same instructor? Here. Okay. Okay. So that is features, and those are the most common types of features that you will see, right? Right. So let me just go back. So the bag of words or numeric input. Numeric input is by far what you will see, right? Numeric feature data. Okay. Almost always what you do is you take these different categories and you map them down into some numeric value before you actually run the machine learning on them. Because machine learning doesn't care what gender is. It doesn't care that it's a string. It wants to know that it can represent, male, female in terms of ones and zeros so that it can use it. Okay. So there's lots of ways to categorize machine learning techniques that exist out there. The most common one that you'll see is classification. All right, what is classification? Very simple. Somebody tell me. Yeah, just like the iris data. Yeah, I just want to classify a class. All right, and those classes don't necessarily. I don't care about any relationship between the classes. I just want, okay, I've got this feature data. It is XYZ or ZZ or ZZ top. Okay? Regression. What is regression? What is regression? This is a good question now. Somebody tell me. Miss Doyle. From now on, from now on, what I'm going to look at someone who's like looking down, waiting to be avoided. And I'm going to single them out. You don't have to answer. Carly, what's up?
I don't know. I said to go back to a previous point of something.
It's when you're trying to predict not a class, a continuous value.
Also based on history.
Yeah. Yeah. Well, no, not based on history. It could be history. It doesn't have to be history. All you're trying to do is predict. Let's say you're trying to predict someone's height based on their weight. All right? So weight becomes their feature vector, right? That's the feature that you're putting in. It's this continuous value. And you're trying to predict how many meters tall they are, how many feet tall, and inches. Right? So you're trying to predict a continuous value, right? Instead of just a discrete class. Right? If it was classification, it would be, are you predicting that they're tall or short? Regression is trying to predict their actual height. There's kind of something that's right in between classification and regression, and it's called ordinal regression. This is when you're trying to predict something that's in a class, but those classes are ordered. They have like a continuous ordering that's in between them. And the classic example of this is trying to predict the rating of someone that they would predict for like Netflix, right? Based on all of these movies, you've rated them as like 4 stars and 5 stars. We're going to try and predict whether you're going to predict this movie as being 1, 2, 3, 4, or 5 stars. Okay? But the order of those classes is important. It's called ordinal regression. Is that okay? Right? It's not just classes that don't have anything between them. Prediction. This is when, based on some past values, what's going to be the next value, right? So the key example here is when you're typing on the keyboard. Or when Google is trying to predict your search characteristics, right? So you start typing in something and it's like, bam, you get all of the hits that happen on Google. That's prediction. Yeah.
Is that like in the stock market when they create some, I guess they use machine learning to predict whether the price are going to go up or down based on the previous.
Yes. The wonderful thing about the stock market is that you create this machine learning model. You have all of this example data and you put it together and you're going to figure out what it does next. And you predict what it does next. And everybody goes, oh my goodness, we're going to make a fortune. And everybody gets your model. And the second that everybody gets your model, the system is changed. And your model no longer works. Somebody else needs to come up with another machine learning model. Because all of the underlying data that you trained with is now different because they're predicting it. All right?
They're predicting that your machine is going to predict.
Yeah, once everybody knows what the prediction is, everybody's doing, this kind of thing, and it changes the whole system.
Well, if everyone thinks you should sell right now, then everyone will sell right now and the market will crash in that area.
Yes.
It's all about timing.
A computer starts buying, right? Whoever has the fastest FPGA implementation starts buying, right? All right. The other type of machine learning is clustering. okay, where, okay, I've got all of this feature data, and I want to cluster it, right? So let's say we were looking at the iris data set, right? And we didn't know all of the labels that were there. All we had were these features. I want to say, let me just build some clusters on it and see which feature vectors just come out to be close together, right? Maybe that's a separate class. If we were to do that Setosa right there, it would just pop out immediately, right? It's so far away from everything else. If you cluster it in the right dimensions, it'll come out. So everything in here is labeled data. You have a label for it. Clustering, you don't have labels for it. Okay? You'll also see this called supervised and semi-supervised, or unsupervised. Okay? Keywords. Next. So let's talk about the most common form of machine learning, which is classification. So let's say we've got these feature vectors in these examples, the Setosa, Versicolor, and Virginica from our iris data set. This would be an example of, let's say, when you have one feature vector and one output right here, essentially when you get another prediction that comes in, some unknown query, you're trying to predict one thing from it, okay? Has everybody got that? Like you're trying to predict, like you have one flower, and I'm trying to predict one thing from this flower. There's another type of classification, which is, let's say you have a sentence, and it's the quick brown fox jumped over the lazy dog. And what you want to do is predict the part of speech. So you want to do some part of speech tagging on this entire sentence. Okay? So you could look at this as a predict one problem, where you're trying to predict, okay, the is an indefinite article, brown is an adjective, over is a preposition, that kind of thing. But it would be much better to look at this entire thing and try to predict this entire output down here. So predict a structure, right? You're trying to predict this entire sentence structure on the output, right? Not just one prediction. This is called structured and unstructured machine learning. The vast majority of machine learning is working on unstructured data, okay? With the big exception of natural language processing. Okay? We are going to talk about unstructured output, okay? If you want to know about structured output, I would love to talk about it. That was my dissertation. Okay? All right. Classification. Let's say we have an unknown. Let's still talk about, let's see the different ways that we can classify the types of machine learning that are out there. Get some keywords on the way. So I have this unknown feature vector. And let's say I have this kind of data set of examples from the iris data set. What would be one way that I could predict whether or not this was Setosa, Versicolor, or Virginica? This right here. So I've got this vector.
You find the distance between your actual value and the other example values, and then you also have to compare them like to each other to see how far apart they are, and then give it a rating.
Do you? I know I like that. Let's say we keep all of the labels that we have. The method that we do is the closest example in the training set by Euclidean distance, right? I take this feature and I take the difference between this and that, right? It's some Euclidean distance in four-dimensional space, okay? Or if that's like blowing your mind trying to think in 4D space, just think, okay, I'll just take the very first two feature vectors and I'll just take the Euclidean distance in 2D space. Whichever one's closer, I'm going to say it's that one, right? So that's method one. Method two, I could multiply the input by the vector 1, 0, 1, 1, and then I could sum up all the values. Okay? So I would do this. I would say, okay, times 1, 0, 1, 1 is 5.7. This is 11.7. This is 14.3. Okay? And then I could come up with this kind of rule set that says, okay, if this is less than 7, I'm going to say it's Setosa. If it's greater than 13, it's Virginica. Else, I'm going to say it's Versicolor, right? So it's Versicolor when it's between 7 and 13. That sum that I take right there. Why do I multiply by 1, 0, 1, 1? Because I decided that I wanted to.
But are you like losing?
I'm losing one feature. Yeah. I am. Maybe that feature sucked. Yeah.
So that's just because those values are so close to one another that
Yeah, I mean, if you look at these are that there's not a whole lot of separability in the second feature, or the first feature. If this is the 0th feature, we'll call this the first 0. Right? So I did that.
You could also like to choose the number you multiply by. That's actually giving them importance of how important it is to distinguish between them.
You're talking about like this value that I choose out here, this sum.
No, if you multiply by I don't know like 2 0.
Oh yeah, maybe this is 2 0 1 0.5.
Yeah, that means that you care more about like difference of the first feature.
It's true, right? But it's a simple algorithm, right? When I do this first method, I have to store, let's say I have 1 million examples of this iris data. I need to store 1 million examples so that when I get an unknown vector, I can compare it to my 1 million examples and take the smallest distance. Okay? Or with this method down here, the only thing I need to store is the vector, my importance vector, and this right here, which is my decisions that I'm going to make based on that importance vector. Okay? So the difference between these two methods, this is called non-parametric, and this one is, surprise, surprise, called parametric. Why? Because I'm parameterizing it, right? Like, I don't need to save my entire data set. All I need to do is for this one down here, I need to train up what these importance values are and what these values that I'm going to be looking for there. I need to find out what those parameters are, but then those are all I need. I get an unknown feature vector, bam. Multiply, accumulate, figure it out. Done. All right? So, parametric, non-parametric. The different machine learning algorithms, right here, a lot of non-parametric things are going to be things like nearest neighbor or k-nearest neighbor, or if you're doing regression, there's this thing called a kernel density estimator, right? Wow. Very cool names, right? Every time you see a machine learning algorithm, you are looking at someone's dissertation that they put together, all right, essentially, right? They were like, I am going to find out the best machine learning algorithm, right? Except no one ever has, right? Because it's application specific. It depends on what your data does. Parametric things are things like decision trees, random forests, this thing called logistic regression, which is not a regression algorithm, it's a classification algorithm. This thing called neural networks. Have you guys ever heard of a neural network? Your brain. Your brain is a neural network. It's the neural network, right? Something we're trying to emulate since the beginning of time and haven't been able to do. Things like Gaussian mixtures, which you'll see all over the place in natural language processing.
What's the random forest?
What's a random forest?
Multiple trees. Just lots of trees together.
I have a slide on it. We'll go over it. Right in between parametric and non-parametric is this thing called a support vector machine. Right? Have you guys heard of a support vector machine? No? Never heard of it? Never heard of it at all? An SVM? SPM? Yes? Something? If you're reading a paper and you find someone that doesn't know a lot about machine learning, they will use a support vector machine, right? And it's not a bad thing to do, right? Because if you don't know a whole lot about machine learning to choose the algorithm you want, the support vector machine is a pretty good option. Okay? And we'll talk a little bit about why that is. So what I'm going to talk about now are the 3 most popular types of machine learning. And we're just going to talk about these at a high level and give you an intuition about what these models are so that you can use them. All right? What do we have? We got 20 minutes left. 24 minutes left of class. Okay, so let's talk about k-nearest neighbor, random forests, and support vector machines. All right, so you guys remember the iris data set. Wonderful. Let's talk about how we would build a decision tree on top of the iris data set. You guys are in data mining, you tell me. What's that? I took it last year. You're in it now, Matt. What would I do? Or I don't know. Do you guys talk about decision trees?
We went over them, but
Not much in detail. Okay.
So we can use different programs. We can use R or RapidMiner to go about it. So if you're using R, you're doing more of the actual programming, or RapidMiner is more GUI-based.
Fair enough. Fair enough. Right? But you at least learned how to use some of the toolkits that are there. to put it together, right? If you want to know how to use some of these algorithms, you need to take the Intro to Machine Learning class. That's not offered yet because I'm still creating it, all right? We'll do that in the future. Okay, so looking at the iris data set, one of the things you could do is we could look, okay, there's this thing called X2 right here, right? So what that's going to do is I'm going to look at the 0, 1, the second feature. And if that feature, let's say that's the petal length, if that's less than 2.45, then I'm going to go down this tree right here. So if it's less than 2.5, I'm going to go this direction. If it's greater than 2.5, I'm going to go this direction, right? Well, it turns out that if petal length is less than 2.45, that's setosa. All right, if it's greater than 2.45, that's versicolor or virginica. All right, so now we're going to go in here and we're going to say, okay, let's look at the X3 right here. That happens to be the petal width, right? So petal width, if that's less than 1.75, then it's mostly versicolor, or most of those are virginica, if I go to the right side for that. And then I can keep going down and coming up with these features that I want to split the data apart on. And it turns out that, if I go down all the way to this leaf, it's virginica. Or if I go down all the way to these leaves, I've got versicolor, virginica. Virginica, don't really know. Versicolor, virginica. Versicolor, virginica. And now this decision tree, it's based on the features that I have. I'm splitting the data. I'm trying to find a split in the data, the best feature that splits my data apart, such that based on this decisions, I can go through and come up with a class very, very quickly, right? So you don't have to understand how we choose the splits on the data or how we choose the features that we're going to split on, but you do have to understand that it's a very, very quick operation that you can go through, right? You make these decisions based on the features that are there, all right? And you split the data up like this. Like if this was a 2D plot, I would split it this way. And then if I'm on the right-hand side, I might split it this way, right? And I'm separating out. I'm just boxing in these classes of examples that I have.
Is it in half?
It's not in halves, but I'm splitting it some way, and it's somewhere along there. Okay. So what those decision boundaries essentially look like are this. All right, so here's my iris data set, and I have my setosa, and then I have my versicolor and virginica up here, right? And I'm just showing petal width and I think petal length down here, right? So essentially what I've done here is the first split that I do is, okay, if the petal width is less than this value, it's setosa. If it's greater than that, it's versicolor or virginica, all right? Then I do another split in the data, right, where most of it is versicolor, and most of this is virginica if I just do a split right across there, all right? And then I do all these little sub-splits. All those little leaves that we were seeing in the decision tree are making these little itty-bitty colored boxes that are in between there, right? But essentially I'm taking up my feature. So this is, when I plot my features that's called the feature space, right? And so the decision boundaries were anything that's now inside of this, it kind of looks brown up here, that's going to be classified as virginica. This will be classified as versicolor, and this is setosa, right? So now if I have some new unknown, I can plot it in there and tell which class it's going to be predicted on the decision tree, okay? But I don't have to do this with just two features. I can do this with all of the different features that I have.
How often do we add functionality like what was the bottom one called, the blue one? Which part is that?
Setosa.
Setosa. The Setosa section covers a huge area where data doesn't fall into it necessarily. Same for the top one. There's these huge areas on top. If you start getting large clusters of data in those regions, can we make our machine learning be like, hey, alert, there must be some new repeatable thing because we're getting a data cluster in this area?
You mean like if we didn't have a label on it? Or
I mean, like we have 3 right now. What if a 4th data cluster started appearing? The more
like we got a new label, right? And it was down here, right?
We didn't add anything in, but as we're testing against things, we're like, well, we're getting a lot of false Sequoia reads because we're getting a lot of reads here, but it's in a different data cluster than the actual. Does that make sense? Do you understand what I'm saying?
No, I don't. But I don't.
Let me point this out.
They have 2
Yeah.
different clusters
Like-
in the same area.
Everything in here we're calling that one. But most of the data is going to fall really close to here if it's actually that plant, right? What if we start getting another cluster that appears right here? Can our machine learning learn that there's a fourth type of plant out there?
There are types of machine learning that can try to learn that there's this new plant that's coming along, right? And that is actually that is something called novelty identification, right? It's essentially like you're learning that this is not something we've seen an example of, right? So it's like based on this model, I think it's Setosa, but it's really far off from anything we've ever seen. So that's called novelty identification, right? There are algorithms for that. Most machine learning algorithms, you're trying to get a model to classify something, right? And so if you don't have labeled data, you can't train it, right? So if I don't have a label of something down there, I don't know what it is. Okay, but that's a decision tree. And we'll talk about that a little bit more in one of the slides. Random forest. What do you guys think a random forest is? A lot of trees. A lot of decision trees. That's exactly right. You make a bunch of decision trees. Each of those trees, you make it with a random subset of all of your labeled training data. Okay? And a random subset of the features that you have. Right? So maybe you have 4 features. We have 150 examples. So we might create a tree, 3 trees. We might create 3 different trees, and we'll say each of them have 120 random examples that I choose from my data set, and 3 random features of the 4 features that I choose right here. Right? If I were to put those together, that would be 3 trees inside of a forest. Okay? What's normally done is I don't create 3 trees. I create something like 200 trees. Right? Just randomly sample through my data set. Then when I have an unknown vector, I send it through each of those 200 decision trees, and maybe it comes back with 95% of the trees say that it's Setosa, 4% say versicolor, and 1% say virginica. Right? So what would I choose? Setosa. What's the advantage of this?
Well, I can see a huge disadvantage that it could be wrong, because it's just probability. But I mean, one of the trees says like that it's definitely virginica. You must have like a reason why. Like,
I see what you're saying. I see what you're saying. It was like it's like if you have a lot of students, and there's one student that you really trust, right? And you're asking these questions and examples, right? Maybe there's one tree in there that you really trust the output of that tree, and the other ones is just kind of noisy output, right? And while that's a possibility, if you're randomly sampling, normally you get a pretty good consensus from the different trees that you have, right? As long as you build enough of them. All right? So this is called a random forest. The key advantage of this is it tells you how confident it really is, right? Because you can say now I'm going to say with 95% confidence that this is Setosa. But I'm saying there's still a 5% chance that it's one of these other classes. Okay?
I guess my concern is with the randomness. Like, why you make it random when you can make a one that actually takes all of the different trees? They just make 200 trees that contain different. You choose them. Because if you make it random, they could be repetitive. So many trees would be saying something, but they know the features.
There's a lot of repetition, but what this does is it prevents you from over-learning on your data set. Essentially what this, because you're randomly drawing, the randomness actually helps you with kind of looking at the bounds of the way that this classifies different things, right? So if you randomly draw from it, you're kind of guaranteeing that you're not going to be over-learning the features that you have in your data set, right? Like I'm not going to, like there may be this like I could draw this really kind of jaggedy line. This is anything below that is virginica. Anything above that is versicolor. And maybe that works for the one sample of labels that I have. But the second I get a new one that's right on that boundary, maybe that falls apart. I've overlearned based on my data set. By randomly drawing from it and looking at this committee, this is actually the optimal way to fight that kind of thing when you have 2 classes that are very, very close to one another.
Just for this class, the very little sections that you just have one yellow, but at the same time you could get a sample that's blue and it's next to it.
Exactly.
So it's,
Exactly. The randomness guarantees that you don't overlearn. Okay, and that's called overfitting. So let's also talk about one of these things that's very, very popular, k-nearest neighbor. Okay, let's say you have 2 different features, x1 and x2 right here, right? And you have these examples that are, here's class A, here's class B, all right? And then you have the star value right here that you don't know which class that belongs from, okay? So you could do a nearest neighbor approach, right? If you did the nearest neighbor, then bam, I think that's the nearest neighbor right there. It's class B, right? But you can also do this thing called k-nearest neighbor, where you're going to look at the 3 closest neighbors to one another, right? So I'm going to find the 3 closest neighbors inside of my data set, and it's these 3 right here. And I'm just going to look for whatever the majority of things belongs to. So if k is equal to 3, then this becomes what? What would I say this class is? B, right? Because I've got 2 inside of the 3. If k is equal to 6, right? Then I'm going to include 1, 2, 3, 4, 5, 6. I'm going to say it's class A. All right? If I have a tie, then you have to build up some logic for that. The best way to build up the logic for that is to essentially default. Once you have a tie, then you bust it down. You say, okay, if I have a tie at k equals 6, I go down to k equals 5 and see if I don't have a tie anymore.
Wait, but how, like, do you just check for 1K? Or do you check for multiple Ks?
Usually you just check for 1k.
So that's like,
You can check for multiple different k's and ensemble them together in the same way that we did the decision trees. And that's called a k-in ensemble.
or how do you choose K? Because that's the key thing.
How do you choose k?
Wouldn't a larger K?
Well, if you choose k too big, you're just like looking at the entire data set.
Right.
Right?
But wouldn't like, I mean, you have to find your
Yeah, that's the most precise
efficiency
example.
versus size, but the bigger it's going to be, the more accurate it's going to be, right?
Nope.
No?
Depends on your data set. The best way to do it, run a bunch of different values of k, see what you get on your labeled data set, and see how it works out. That's called a grid search. You essentially, you put a grid for all the values that k could be, and you're like, okay, I'm going to go through and find the optimal one. So based on what we know is labeled data. That's all we know. That's all we got. That's the only examples, all right? We're a baby that's looking out for examples to learn something, all right? All we have are the labels. So we go out and we figure them out from this. So that's how we choose the optimal value of k. And that optimal value of k depends on your application.
Yeah, it's probably not well said, because if you had 50 samples of each of the 3 and then you check the whole set, then it's going to be
Right.
all
Yes. If you make k too big, then it's like, oh, well, you know, let me get the 150. Yeah. You get whatever your class diversity was, right? What's also a problem here? What if you have a lot of examples of class B, but not a whole lot of examples of class A?
then samples wrong.
Yeah. Then you sampled incorrectly, right? But maybe it was cheaper, right? Like you had to pay someone to like get these examples and the labeled data for you, right? So there's a lot of things you have to take into account here, right? But if you choose k small enough, I mean, like let's just be practical now. If you choose k small enough, 3, 5, it's probably pretty good. Okay?
In this case, what we should choose?
I don't know. Depends on what that star should be. It's right on the border, right? Here's the thing. Machine learning is not magic, all right? If you can't look at that, like if you look at that, what should that be in your head? You think it's B. I think it's A.
And yeah, there's.
I was actually just like playing devil's advocate, right? Because you can make an argument for either, right? It's right on the border.
Well, there's more closer to A.
There's more closer to A for k equals 6. Okay? If you as a person can't like sit down and kind of figure out what's going on, a machine's not going to be able to do it. So here's what that decision boundary looks like for the iris data set. If we look at, I think I used petal width and petal length, and we use k equal 5. Okay? This is what those decision boundaries look like. So instead of those nice like decision boundaries like this, you get decision boundaries that look they can be whatever they need to be based on your labeled data, right? So if you have enough data, k-nearest neighbor is if you have enough data examples and not a whole lot of features, right? So less than 5 or 6, k-nearest neighbors is the optimal method for you. It is the best way to do some of this machine learning. Okay, because it can draw these arbitrary decision boundaries, right? Like this looks like a pretty good breakup of the data. Maybe I wouldn't agree with this over here, but there's something there. I'm getting examples over here that are kind of clustering together, right? Okay. If I were to,
In that one, k equals 5.
in this one, k equals 5.
Then why is that like little green circle there? Does it have like 5?
Oh, this one right here?
Oh, it's 1, 2, 3, 4, 5.
1, 2, 3, 4, 5.
Yeah, like
Oh, well, that's part of my training set. Is this thing right here? Right. So essentially, there's like a little itty bit of values right around here where k equals 5 actually. I'm projecting this down into 2 different things, but I've trained this on more than 2 features.
Oh, that's a 3D.
Yeah, it's 4D, but I'm projecting this decision boundary down into 2 dimensions, right? Because I can't visualize what those boundaries look like in 4 dimensions. I can't show it to you. All right, but they do exist. Okay, support vector machines. Essentially, a very, very intuitive look of a support vector machine would be to essentially what we're going to do here is we're going to try and find a vector that I can draw on my feature space and separate the classes, right? So for a linear support vector, I'm going to look for a line that I can draw between the classes, right? A line that I can draw that separates out my classes, all right? You'll also see something called support vector machines with a radial basis function. It's just Gaussians that they're looking down. And essentially what this done is it makes a line right here, which is it's like a Gaussian. If you were to draw like 3 Gaussians down in 2-dimensional space and kind of trace where they're bigger than another one, right? Or there's also this thing called a sigmoid, which I won't really get into. But it's essentially, it's a different kind of kernel that you're drawing, right? So the intuition here is that we're going to try and find something where I can optimally separate my 2 classes. What do I mean by optimal? Well, let's take it, if I'm just trying to tell the difference between, say, this Versicolor and Virginica versus Setosa down here, I could have drawn this line like where it is. I could have drawn it like down here, right, across it there. I could have drawn it like across this. Why did I choose this?
It's exactly in the middle.
Because it is exactly in the middle, right? These classes are completely separable with these 2 features, right? And essentially what I'm going to look at is I'm going to maximize the margins, right, between each of the classes. The margin being the difference between what I draw and the actual clusters that are there, right? So essentially all I really need to know are a couple of the vectors, or sorry, a couple of the points that are on the edge of the classes. And then based on those, I'm going to do the max margin in between them, right? I'm going to choose a line that maximizes that margin, right? And it's the same thing with these Gaussians and sigmoids, right? Like it's essentially, it's a different function that I'm drawing a boundary around, but it's still trying to maximize the margin between the 2 classes, okay? So let me do just a very quick demo of support vectors. And I'm going to use something, this little svm GUI.py. I'll change directory. Okay, so Python 2.7 svm GUI.py. All right, so, oh great, that's a wonderful little thing. So essentially what I can do here is I can click onto here and I can create one class right here, and then I can right click and create another class, right? So this is a binary classification, right? It's either a 0 or a 1, right? In this case, it is black or it's white, okay? So I'm trying to predict the color of these dots. Okay, so what I can say here is fit. So here's a support vector machine. What it did is it found the edges of the clusters right here. So each of these data points right here that's on the edge is a support vector. That's where it gets its name, right? These are the support vectors that it's going to use. And because this is a linear, right? So I've actually chosen this to be linear. Right down here, you didn't see it. It chooses that right there. So I can add some, let's say I add a point right in there, right? Well, then I need to retrain, right? Or if I add one that's right here. What happens if I put a wrong class right there? It doesn't like it, right? Like it's going to misclassify that point, right? But it misclassifies that point. It essentially, like at the expense of getting that wrong, it's going to make sure that it gets most of this right. Okay? So the problem here is that I need something that can create something more than just these linear vectors if I want to be able to classify that thing right there. So maybe I want to use Gaussians. Right? So there's a bunch of different parameters that I can use right here, such as there's a C and a gamma function right here. So if I change gamma just a little bit, I can say fit, and it'll actually give me Gaussians that look like this. Right? So I've gotten that one correct. Right? I've got these little boundaries that I've done right here. Right? I can also choose a polynomial. Right here, right? So this is essentially, there's a polynomial that it tries to fit right here. And it uses these support vectors and that one right there, so it can bend this over, right? If you have noisy data labeled in your data set, it's noisy, it's not exactly what you want, this method is going to learn that noise, okay? It will learn anything you tell it, right? So if you have noise in your labels that maybe it's, it's incorrect, it'll learn that. Yeah.
So in this case, you're choosing Gaussian earlier based on outliers specifically in this case. But is there other criteria that you would switch between those models for? Choose one or the other, or is it just to handle that type of thing?
It's application specific. It's if you visualize part of your data, right, and you see that, hey, this looks kind of linear. If it looks kind of linear, use linear, right? The reason is that because it'll generalize. Like if it is a linear relationship that you're modeling, then linear is the way you want to go, right? Usually what we have, there's some linearity and some non-linearity there. And so a sigmoid is usually the best way to go. Essentially, a sigmoid function is something that looks like this, right? And so depending on where you're trying to fit that sigmoid, you can have like a cubic, or it almost looks quadratic if you really, really zoom into it. It's got this little thing. Or it can also be logarithmic at this point up here. Or it can be linear if you're looking at it like right in the middle, right? So it kind of fits itself to the data that's there. How are we doing on time? We are out of time. So that's good. We got to SVM. Next time we will get into the pitfalls of machine learning, and we'll go through the toolkit. Good?